Welcome to this comprehensive masterclass on LeetCode problem number 21, Merge two sorted lists. In this video, we will explore every aspect of this classic linked list interview question, including detailed problem understanding, multiple solution strategies, step-by-step dry runs, as well as Python and Java implementations. By the end, you will know both iterative and recursive methods, learn how to handle tricky edge cases, understand why certain patterns are used, and become confident solving similar questions in interviews. Let us dive right into the world of linked lists and merging techniques. Let's thoroughly review the problem statement for LeetCode problem number 21, merge two sorted lists. You are to combine two given sorted linked lists, called list 1 and list 2, into a new sorted linked list. The merged list should maintain the sorted order and be composed of nodes taken from both provided lists. Let us walk through all examples provided. In example 1, merging 1, 2, 4 and 1, 3, 4 produces 1, 1, 2, 3, 4, 4. We start by comparing the heads, both 1, so 1 is added twice. Then we proceed to 2 from list 1 and 3 from list 2, taking 2, then 3, and so on, always picking the smallest node at every step until both lists are exhausted. In example 2, both input lists are empty, so the result is simply an empty merged list. In example 3, the first list is empty and the second list is 0, so the merged list is just 0. Let's continue by examining the constraints and important edge cases for LeetCode problem number 21. Both input lists can have up to 50 nodes each, and each node value ranges from -100 up to 100. Both lists are already sorted in non-decreasing order, which is a key property we can leverage in our solution. Key edge cases to consider include when both lists are empty, when one list is empty and the other is not, when all values of one list come before or after the other in value, when the lists are made up of only identical values, and when there are negative, 0, or positive values. Thinking about these scenarios is crucial to ensure a robust and bug-free implementation. For LeetCode problem number 21, there are several reasonable strategies to merge two sorted linked lists. The most common is an iterative two-pointer approach, where we scan both lists simultaneously, always comparing the current nodes and attaching the smaller one to our new merged list. By maintaining a dummy head pointer, the process becomes clean and avoids extra conditionals. The recursive approach uses the same logic, breaking the problem down into smaller subproblems by always attaching the node with the smaller value and recurring on the rest. In practice, both methods directly relink the existing nodes, avoiding unnecessary memory allocations. While it is possible to solve this by creating brand new nodes, that wastes memory and is not what the problem asks. Thanks to the lists already being sorted, each merge step is very efficient. Ultimately, either iterative or recursive merging is the recommended strategy. Let's break down the merging algorithm for LeetCode problem number 21 step by step. We start by initializing a dummy node, which provides a simple way to build our result list without worrying about special cases for the first element. We then keep a pointer, called tail, that always points to the last node in our merged list so far. While both input lists have remaining nodes, we compare their current nodes' values, always linking the smaller one to tail.next, and advancing the corresponding pointer. This ensures the merged list remains sorted at every step. Once one list runs out of nodes, we simply attach the rest of the non-empty list to the merged list. Finally, we return dummy.next, as the dummy was only a convenient placeholder. The dummy node trick is essential, as it avoids handling the empty result case separately and ensures cleaner code. This method is efficient, straightforward, and optimal for this problem. Here is the Python solution for LeetCode problem number 21, merge two sorted lists. We first define the list node class, which represents a single node in the linked list. The solution class contains the merge two lists method, which takes the heads of the two input lists as arguments. We create a dummy node to serve as the starting point for our merged list and initialize a tail pointer to help build the result efficiently. While there are nodes in both lists, we always attach the node with the smaller value to our merged list, moving the pointer forward for the list we just took from. Once one of the lists runs out of nodes, we attach the rest of the other list to the merged list. Finally, we return dummy.next, which points to the head of our new merged list. This approach efficiently merges both lists in place, reusing existing nodes and achieving extra space usage. Here is the Java solution for LeetCode problem number 21 with the same logic as the Python version. Both the listNode class and solution class are provided. The Java version uses type annotations and requires an explicit listNode definition. The merging logic remains unchanged, maintaining pointers to the heads and always attaching the smaller value node to our merged list. The use of a dummy node, tail pointer, and in-place merging is identical, but with explicit null checks and variable declarations as required by Java syntax. This highlights how the same strategy works across languages, adjusted for syntax and typing. The key differences are static typing, class definitions, and how null is handled, but the core algorithm is identical. Let's look at a step-by-step walkthrough of example 1 for LeetCode problem number 21. We begin with list 1 as 1, 2, 4, and list 2 as 1, 3, 4. Initially, we compare one from both lists and attach one from list 1 first. Next, we still have 1 in list 2 and 2 in list 1, so we attach 1 from list 2. We then compare 2 and 3, attaching 2. Then 4 and 3 gives us 3 next, so we attach from list 2. Afterwards, both lists have 4, and we choose to attach 4 from list 1. Now, list 1 is empty and only 4 remains in list 2, which we attach at the end. Our final merged list is 1, 1, 2, 3, 4, 4, which preserves the sorted order. This process demonstrates the core logic, always taking the smallest available node at each merge step. Continuing our walkthrough with more examples from LeetCode problem number 21. In example 2, both input lists are empty, so the merging process immediately returns an empty list. In example 3, list 1 is empty and list 2 contains a single 0, so the merged list is just 0, copying all remaining nodes from list 2. Considering another edge case, merging 1, 2, 3, and 4, 5, 6 results in all elements from the first list added first, followed by all elements from the second list, since all 1, 2, 3 are less than 4, 5, and 6. These cases highlight how merging handles empty lists and non-overlapping value ranges robustly. Now let us analyze the time and space complexity for LeetCode problem number 21. Each node from both input lists is visited exactly once while building the merged list, and the cost of each merge step is constant. If the lists have lengths n and m, the algorithm performs precisely n plus m operations, making the overall time complexity O of n plus m. For the iterative solution, extra space cost is constant, O(1), since we use only a handful of pointer variables. For the recursive solution, the function calls accumulate on the call stack, leading to a worst-case space use of O(n plus m) if every node causes a recursive call. No extra memory is used for new nodes, as we reuse the existing nodes. This approach is both optimal and elegant. Comparing both approaches for LeetCode problem number 21, both the iterative and recursive algorithms have the same linear time complexity. However, the iterative approach is preferred in practice because it has constant space usage and will not encounter a stack overflow, while the recursive method can exceed call stack limits on longer inputs. Both methods are optimal in memory since they reuse all nodes rather than allocating new ones. The dummy node trick streamlines pointer management. In conclusion, merging two sorted lists this way is a foundational pattern that underpins more advanced linked list problems, and this solution is both efficient and robust. Let us finish with some common variations, pitfalls, and practical tips for LeetCode problem number 21 and similar problems. This merging pattern appears in more complex scenarios, such as merging k-sorted lists, and problems like LeetCode problem number 23. Or as part of linked list sorting routines like problem number 148. One typical mistake is mismanaging pointers, which can cause infinite loops or skipped nodes. Always remember to handle node references diligently and prefer pointer relinking to creating new nodes unless specifically required. In interviews, clarify requirements about node creation. The dummy node trick is a key pattern to master. Finally, make sure to clearly explain your thought process, especially how you handle base cases and edge conditions, to demonstrate your thoroughness and mastery during interviews. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!